Hello everyone, welcome to my video on related rates. So if you're struggling with related rates, it's normal, it's a difficult topic. Hopefully by the end of the video, you'll have a better idea or more clarity on how to solve related rate problems. So first off, recall that we're going to be using chain rule to solve related rate problems, but we're going to use it specifically in the Leibniz notation. So we're going to use dy over dx, that's equal to dy over du times du over dx. Notice that if the du's cancel, you're left with dy over dx, and that's equivalent to the left-hand side of the equation. So this is what we're going to do. We're introducing a new parameter. The new parameter that we're going to introduce for related rate problems is the parameter time, t. So we want to know what happens as things move and change with respect to time. So this is our goal. So I just want to mention that I think of it, so there's different ways of solving the problems, but I think of it as a Cartesian plane. So we have the x-axis, the y-axis. So whenever we have any motion, and this is the origin, so I tend to set things at 0. Whenever we have motion or anything that's moving, or we're calculating the distance of something that's horizontal, I'm going to use the parameter x, okay? And anything that's vertical or moving in the vertical direction, I'm going to be using the variable y, okay? So I just want to keep that in mind. You don't have to do it this way. This is just the way I'm going to label my problems. The other thing I want to mention is that if an object is fixed, so it doesn't move. Think of like the height of a table. If we have the height of a table, throughout as time passes, the height does not change. So these would be variables which are fixed. Okay, so if your variables are fixed, as in they don't change or they don't move throughout the entire duration of the problem, then we're going to label them x, y, and z. So they don't move. But if there's movement, or if something's changing, you could think of it as maybe you're looking at the height of a person. People grow. So since there's a movement or there's a change in height, this would involve derivatives. So we're changing dx dt, dy dt, or dz dt. So everything's with respect to time. So instead of deriving with respect to x, which is what we've seen up until this point, we're going to be more specific. We're not going to use the prime notation. We're going to use Leibniz notation to emphasize on the fact that we're deriving with respect to time. So this would be a movement that's in the x direction, any horizontal movement. Anything that's moving in the y direction would be dy dt, any vertical movement. And dz dt could be another parameter depending on the situation that we're dealing with. Okay, so keep that in mind. If it's fixed, it's going to be x, y, z. If there's movement involved in the situation, it corresponds to derivative, a rate of change. Okay. So another thing I want to mention is that we've seen implicit differentiation. So for implicit differentiation, let's say we had y squared, and we're deriving with respect to x. So we've seen this, d dx. Since the derivative doesn't match the variable that we're using, because we're deriving with respect to x, and we have a y, well, this is equal to, the derivative of y squared is 2y, times, I would write y prime, usually. But we could think of it as the derivative inside, and really what we have is dy over dx, the derivative of y. So we are applying chain rule. This is what we're using over here. So this is the first term, 2y is the derivative of y squared, but since we're deriving with respect to x, a different parameter, we have this derivative dy over dx that pops out. We're doing the exact same idea, but now instead of deriving with respect to x, we're deriving with respect to time. So we have d dt of, let's say, r squared. We're going to be dealing with shapes like volume, spheres, surface area, which include radius. So r is a constant that we're going to be using often. So if, let's say, you have the derivative of r squared and you're deriving with respect to time, because related rate problems, we derive with respect to time, this would give us 2r. But since the parameter does not match the derivative, we have to apply chain rule and multiply it by dr dt. Same concept as what we have up here. But just keep in mind we're going to be deriving with respect to t. Okay, so let's look at a strategy to solve related rate problems. So the issue with related rate problems is that there's no real structure that you could follow to solve the problem. Every scenario is different, so you'll have to make sure you understand the problem when you're attempting it. So a strategy that we could follow is, first off, read the question carefully. It's super important you read the question carefully and identify your variables. So Is the object moving in the x direction? Is it stable in the or fixed in the y direction? So on and so forth. Identify the variable, what's given in the problem, what is the question asking for. Step 2, draw a diagram. Take the moment, take the time to draw a diagram. I think it's super important and helps in the problem. Step 3, write down your equation. So if the equation is talking about, I don't know, a balloon that's being filled with air, well, a balloon, let's say it's a spherical balloon, a perfect sphere, write down your volume of a sphere. If you're talking about the amount of air in the balloon, we're going to use a sphere. So write down the volume of a sphere equation. So you have to write down your equation pertaining to the situation. Step 4, take the derivative on both sides of the equation with respect to time. So as things are, let's say you have your balloon and it's inflating, it's changing with respect to time. Go ahead, take the derivative on both sides of the equation with respect to t. Lastly, make the appropriate substitution and solve for the unknown. So we're left with solving. So keep in mind we're dealing with a lot of shapes, so let me give you a reminder of the formulas that we're going to be working with. So here I'm providing you a formula sheet. So the top 8 shapes are 2-dimensional shapes. So you have your A, which is the area, P, which is the perimeter of those shapes. You also have to know the formulas for the 3-dimensional shapes. So the bottom 8 shapes are 3-dimensional shapes, and LA stands for the lateral area, TA stands for the total area, and V is the volume of those shapes. So for related rates, we're going to have to know these formulas, so write them down, make sure you have them memorized. So in this example here, a large stone is dropped into a lake causing circular ripples, and the radius of the circle is increasing at a rate of 1 meter per second. How fast is the area of the ripple increasing when the area is 25 pi meters squared? So this is an example of a very typical easy related rates problem. Let's just get a feel for it. So first of all, a large stone is dropped into a lake causing circular ripples. So we have keyword here is circular ripples. So we're dealing with circles. Let's go ahead and draw that. So we're dealing with the circle. The radius of the circle is increasing at a rate of 1 meter per second. That's the next key. So we have radius increasing, and a key word here that we have to identify is the word rate, a rate of 1 meter per second. So a giveaway is the units. Look at the units to identify whether the variable is fixed or if it's moving. So we have our radius here, let's call that r, and the radius is increasing at a rate of 1 meter per second. So is the 1 meter per second your variable r? Is that the radius? Or is that the derivative of the radius? Is there motion involved? This is what you have to think about. Well, the radius is not 1 meter. The radius is increasing at a rate of 1 meter per second. There's movement involved. It's getting bigger. This means that we're dealing with the derivative. So the derivative of the radius with respect to time, because there's motion involved, is 1 meter per second. Okay, and look at the units. The fact that we have meters per second is the giveaway that it's a derivative. Okay, because this is the velocity. It's the change, the rate of change. Okay, so the units also give it away. If it was fixed, it would have been just 1 meter, right? So let's use this notion to continue. So we know that the derivative with respect to time is 1 meter per second. How fast is the area of the ripple increasing? So now we're asking about the area. The question asks, how fast is the area changing? So is that talking about your area, or is it talking about the change in the area, the derivative of the area with respect to time? Okay. Since it's asking how fast is the area changing or increasing, that's dA dt. The question's asking us for dA dt. That's our goal, to go find dA dt. It's not asking us what the area is. It's asking how fast is the area changing. There's motion involved. That's the derivative. So how fast is the area of the ripple increasing when the area is 25 pi meters squared? They actually look, well, if you look at the units, it's meters squared, so right away that gives away that it's area. But also we can know that this is fixed because it's saying specifically when the area is an actual value, 25 pi. So we actually know the area. So the area of the circle has to be 25 pi meters squared. Okay. So this is identifying the variables. So all we're missing is the radius. Next, what we have to do is we did our sketch. We have our circle with the radius r. Next, we write down our formula. What are we talking about here? Well, we're talking about the area of a circle. So right away, go write down the formula for the area of a circle. Let me do it over here on this side. So we know from our formula sheet that the area of a circle is pi r squared. Step, I believe it was step 4, says to take the derivative with respect to time on each side of the equation. This isn't always the most efficient way, but I think this gives us a good idea. I would always write down my formula, and then the next step, just take the derivative with respect to time. So deriving this with respect to time, we get d dt of a and d dt of pi r squared. Okay, so the derivative of the area with respect to time is what the question's asking us for. So we can't substitute anything here. And now we have to take the derivative with respect to time of pi r squared. So this is pi times r squared. Are we using product rule here? Because we might have to use product rule. Well, no. Pi is a constant. It's a constant multiple, so we're just going to leave the pi. Whenever we're taking the derivative of a constant multiple, we ignore it. All we're dealing with is the derivative really of r squared, which is what we saw in the intro. So the derivative of r squared with respect to time, with respect to t, is 2r times, since t and r do not match, it's not the same variable, times dr dt. Okay. So in order to answer this question, all we need is the radius and all we need is dr dt. This is what gives us, because this is what the question is asking us for. It's asking us to go find the derivative of a with respect to time. In order to do that, we need the radius, we need dr dt, and we're done. Well, dr dt we have. That was information that was provided in the problem. All we're missing now is the radius. How do we go find the radius? Well, what information haven't we used yet? We haven't used the area. So how do we do this? Let's simply take the area formula and plug in what we know. The area of a circle is pi r squared. So before we take the derivative, we're going to use the area to find the missing value of r, to find the actual radius. So area is 25 pi. Let's substitute that in. Equals pi r squared. We divide both sides by pi. Giving us 25 equals r squared. And then we take the square root on both sides, leaving us with r equals 5. Technically it's plus minus 5, but the radius can't be negative. We can have a negative distance, so we're going to take the r to be 5 meters. So we actually have the radius. We have the rate of change of the radius. So we're done. We could plug everything in. So dA dt is equal to pi times 2 times the radius, which we just found was 5, times dr dt, which is, given in the problem, 1 meter per second. This gives us an answer of 10 pi. And since we're changing the area, it's meters squared per second. Okay. And that's our final answer. So the area is 10, let me write it up here because I think it's cut. 10 pi meters squared per second. So in this example here, we have a 25-meter ladder which is leaning on a wall. The top of the ladder is falling at a rate of 2 meters per second. A. How fast is the foot of the ladder moving when the foot is 7 meters away from the wall? Very typical question. Let's go ahead and sketch it. So we have our wall here in red. We have our ladder up here. And this is the floor. So this distance here, the left side, so the shape that you should see that we're working with is a triangle. The left side of the wall is vertical, so I'm going to call it Y. You could call it whatever parameter you want. The base is a horizontal distance, so I'm going to call it X. And I'm going to call the length of the ladder, let's say Z. Okay. So we have a 25-meter ladder which is leaning on the wall. So the 25 meter, what does it correspond to? That's what you have to ask yourself. So take a moment, think about it. This is the actual fixed distance. Look at the units, it's meters. It's not meters per second, so we're talking about the fixed distance for the ladder. The ladder, we denoted it as Z, so Z is equal to 25. Okay. So this part's done. the top of the ladder is falling at a rate of 2 meters per second. So we're talking about the top of the ladder up here, and it's falling, it's going downwards. So we have to figure out, does the 2 meters per second correspond to y, or does it correspond to dy dt? Is the 2 meters per second fixed distance? Is it saying that the length or the height of the wall is 2, or is it saying that the ladder is moving? Well, here the top of the ladder is falling, so there's a motion involved, therefore this is a derivative. It's not the parameter y. Another thing to keep in mind is the fact that the top of the ladder is falling. This means that the distance here is getting smaller, meaning that it's going in the negative direction. So we have to put a negative in front of the 2 meters per second, okay? Because it's moving in the downward direction. So the 2 meters is done. And now it's saying how fast is the foot of the ladder moving when the foot is 7 meters away from the wall. So the foot of the ladder, how fast is it moving? So if we have a ladder here and the top part is falling, think of the base. Think in which direction it's falling or it's moving. Is it moving towards the left or to the right? Okay, so take a moment, think about that. And it's telling us that the foot is 7 meters away. So look at the units, it's meters, it's not meters per second. So that's just a distance, so it's giving us the x value. X is 7 meters. Okay. So we have the derivative with respect to y. So now what your job is it's to figure out which formula are we using here. We're talking about all the three sides of a, give you a hint, 90-degree triangle. Are we using area formula? Are we using perimeter? What's going on here? So what you have to catch here is the fact that you have a relationship between y, x, and z. Do you know a formula that involves y, x, and z? Or the two sides and the hypotenuse, maybe. Let me give it away. This is a Pythagorean theorem problem. So here we have to use the Pythagorean theorem formula, which is typically shown as a squared plus b squared equals c squared. Okay. You do not want to use more parameters on top of the ones that we labeled. So do not use a squared plus b squared equals c squared. Use the parameters that are actually used in the problem according to your sketch. If you wanted to call this a, b, and c, then that's fine. You could do that as well. But based off the parameters that I'm using, because I'm going to stick with x, y, and z, we have really x squared plus y squared equals z squared. That's the formula that I'm using. I'm using Pythagorean, using the parameters that I labeled. Okay. Let me just move the dy over dt down here. And the next step is to take the derivative on both sides of the equation that we're using with respect to time. So we're going to take the derivative, the t of x squared plus y squared, and the derivative with respect to t of z squared. Okay. And similar in the earlier problem when we had to take the derivative of the radius, same concept. So we're taking the derivative of the x squared with respect to t. The parameters do not match, so we have to apply chain rule. So the derivative of x squared is 2x. But we're not deriving with respect to x, we're deriving with respect to t. So we have to multiply by the derivative of x with respect to t, or x prime. I'm not going to use the prime notation because I want to emphasize on the fact that we're deriving with respect to time. So dx dt, Leibniz notation. Plus, what's the derivative of y squared? Well, it's 2y. But now we have to apply chain rule because we're deriving with respect to t. T and y are different variables, so we get times dy dt. And that's equal to, same idea over here. We're taking the derivative with respect to time of z squared. The derivative of z squared is 2z times, since the variables do not match, dz dt. Okay. So the question is asking us how fast is the foot of the ladder moving? So the only parameter we're missing here, like to answer the question, is we want the foot of the ladder. As this falls, I asked you to think about it. Which direction is the foot of the ladder moving? Well, as the ladder falls, this is going to go, it's going to move towards the right, the base of the ladder. Okay, so this is a movement in the x direction. So the question, what it's asking us, is for dx dt. So in our equation here, what we're looking for is dx dt. That means to get this, to isolate the dx dt, we need to know x, y, dy dt, z, dz dt. So now let's go through all the parameters individually. X, do we have the distance X? X is 7, it was given in the problem, so we're good. This is fine. Y, do we have Y? Well, Y we're missing, we don't have Y. So we'll put this on pause, but there's a way to find it. Dy dt, do we have that information? Yes, that's given here. Dy dt is given, so we have that. Z, do we have Z? Yeah, that's given. And dz dt, we don't know that. So the two issues, or the two things we have to go find, are Y and dz dt. So let's start off with Y. Let's go find our Y. How do we find Y? Well, we know the base is at 7 and the hypotenuse is 25. So we just applied Pythagorean theorem to find the missing variable. So let me do that on the side. So z squared equals x squared plus y squared. 25 squared equals 7 squared plus y squared, which is what we're looking for. 25 squared is 25 times 25, it's 625. 7 times 7 is 49, plus y squared. Subtract over the 49, giving us, let me take my calculator. 625 minus 49, we get 576. That's equal to y squared, and then square root, giving us 24. Okay, so we're taking the square root. It's technically plus minus 24, but we can't have a negative distance. That doesn't make sense, so we'll keep it as positive 24. So we actually found the value of y using just Pythagorean theorem as we saw in high school. Okay, so the height of the wall is 24 meters. So that's done. The next parameter that we need, or the next variable that we have to look for, is dz dt. And this is one that you have to think of it based off the problem. So z is the length of the ladder. dz dt is the derivative, meaning the change. How is the ladder, or the length of the ladder, changing as it's falling? Think about it. So if I have a pencil over here and my marker, let's say, falls, what do we know about the length of the marker as it's falling or as it's moving? Did it change? The answer is no. So since there's no change throughout the entire process of the length of the ladder, that's telling us that the derivative, or the change with respect to z, the actual distance of the ladder, is 0. And that's what's difficult to find about these types of problems. So you really have to understand the situation, that what's going on. So the change in z is just 0. And now we have all the values, so we could go ahead and find the derivative of x with respect to time. Okay. So 2 times x, we know is 7, times dx dt is what we're looking for, plus 2 times y. Y we found was 24. dy dt is given. dy dt is given as -2. And 2 times z, it's 2 times 25 times 0. So this whole right side of the equation is 0. Here we get 14 dx dt plus 2 times 24 times -2. We get, what is that? 48 -96. And now we just solve for the missing variable. I'm just gonna erase and give myself a bit of room, and we'll do it up here. So 14 dx dt minus 96 equals 0. We bring the -96 over, we get 14 dx dt is equal to 96, and dx dt dividing by 14 on both sides gives us 96 divided by 14. Let me take a calculator. I'm getting 6.8. Let's say 8, 6. Okay. So does that answer make sense? So we found, this is meters per second. So we found that the change in x with respect to time is 6.86 meters per second. The fact that it's positive tells us that it's moving in the positive direction towards the right. Does that make sense? Yes, because as the ladder falls, we would expect it to move towards the right, not the left side. If it was negative, that means it's going towards the, let's say the zero of our Cartesian plane. So it's not, the distance here is not getting smaller, it's getting larger, so we would expect it to be positive. Okay. So now we have the exact same example, but part B, how fast is the angle between the ground and the ladder changing? So the angle over here, how fast is that changing throughout the process? So first of all, is it getting bigger or smaller? This is what you should ask yourself. Do you anticipate your answer to be positive, getting bigger, or smaller in the negative? Well, as the ladder falls, we would expect the angle to get smaller. So I do expect when we finish solving that my answer is negative. So again, how fast is the angle changing? So the question is not asking for theta, it's asking for the change in theta, because there's a motion involved, there's movement involved. So it's asking for d theta dt. Okay, so we're working with a right angle triangle, and now we're dealing with angles. We're not dealing with how how much dx dt is changing, we're dealing with an angle. Which formula should we be using if we have side lengths involved and angles involved? Well, this is where our trig formulas come into play. So you have to remember your trig formulas. And we could use any which one. Our trig ratios are sine theta equals our SOHCAHTOA. Sine theta equals opposite over hypotenuse. I think I'll just use sine. You can use sine, cos, or tan, doesn't matter. I'm going to go with sine. So sine theta equals opposite over hypotenuse. Okay. So this is our formula that we're using. It has an angle involved, so this is good. The only thing is I'm going to label it with my values. So if this is the angle, I'm using this angle here. Where's my opposite side? Where's my adjacent? Where's my hypotenuse? Well, with this angle, the hypotenuse is always the longest side. So this is your z. This is the hypotenuse. It's the longest side. It's always across the 90 degree. The opposite side to this angle is the side on the opposite end. So this would be where the y is. And the last one is the adjacent, the side touching the angle that we're talking about. So that's our x. So this is our adjacent. Okay. Because I chose sine, you could have chosen cos tan. Because I chose sine, I'm using opposite over hypotenuse. So I'm doing y over z. Okay. Notice that we know the variables of y and z. It's 24 and 25 respectively. But do not use that. Leave it as x and y. Treat them as variables. Do not treat them as known values, okay? Because then you're going to get a constant, and then when you take the derivative, the right hand side is going to disappear, and we lose. We end up with the wrong conclusion. So leave it as y and leave this as z as is. Once you take the derivative, after you can worry about plugging your variables in. So let's go ahead and we have our equation. Let's go take the derivative with respect to time on both sides. So we're deriving d dt of sine theta, and that's equal to d dt of y over z. So the derivative of sine theta with respect to t is sine theta, the derivative of sine is cos theta, times since theta and t are two different variables, we're multiplying by d theta dt. And now we're taking the derivative with respect to time of y over z. So what we have here, y over z, is a quotient rule. So we're taking the derivative of the top. So quotient rule, remember, it's f over g prime equals derivative of the top times the bottom minus derivative of the bottom times the top. All that over the bottom squared. So that's what we have to do here on the right hand side. So if you take the derivative of the top with respect to t, it's dy dt times the bottom, which is z, minus the derivative of the bottom, so dz dt, times the top, y, all that over z squared. So let me just erase and give myself some room. Over z squared. Okay, so we took the derivative with respect to t on both sides. Now we can start worrying about plugging the variables in. So first thing, cos theta. We have to go get cos theta because our job, the question is asking for d theta dt. So that means we have to get cos, we have to get dy over dt, z, dz over dt, y over z squared. But we have all the information already. We solved it from before. So dy over dt we saw was -2. That was given in the problem, so we could start plugging that in. negative 2 times z we know is 25 minus dz dt, the change in z with respect to time we know is 0, times y, which is 24. All that over z squared. Z we know is 25, so it's 25 squared. And that's equal to d theta dt. But we have to figure out the cos. How do we get cos theta? Well, what's the formula for cos theta? Cos theta, using our trig properties, we know that cos theta is equal to adjacent over hypotenuse. Soft cut to adjacent over hypotenuse. We know the adjacent is x and the hypotenuse is our z. And now we could actually substitute the actual values. Now that we took the derivative, now you could substitute. Okay. So remember, in our strategy, substituting the variables was one of the last things to do. Okay, so don't do it too early. So x we know is 7, z we know is 25. So we have 7 over 25. Okay. So I'm running out of room. I'm just going to write 7 over 25 instead of cos theta because that's what it's equal to. And now we're going to multiply by 25 and divide by 7. So let me erase just to give myself some room and continue up here. So from this equation down here, we have 7 over 25. We're coming up here. Times d theta dt is equal to negative 2 times 25 minus 0, because 0 times 24 is 0, over 25 squared. So one of the squareds cancels with the 25, that's good. And now we're going to multiply by 25 and divide by 7. We're essentially cross multiplying, giving us, let me get some room, d theta over dt equals 25 times negative 2 over, and the 7 is going to drop down here, 7 times 25. The 25's cancel, we're left with negative 2 over 7. So the change in the angle is negative 2 over 7 radians. So this, as we would expect, the change in the angle is getting smaller. So the fact that it's negative is reassuring.